Anyway, well, like I said, in chapter 27, I introduced the concept of Ohm's law that delta V is I times R. And the quantities that are important in looking at a circuit are I, delta V, and R. I also went through and described where the idea of current came from. I came up with a simple equation that the current can be written as N, Q, V sub D, and this is the magnitude, which is the drift velocity. This is the magnitude of drift velocity times A. And this is delta Q over delta T. Or really, to be more exact, I should call this dQ dt. Okay. I want to give you a little more general description of I and J. But yeah, by the way, I also defined J to be defined as I over A. And I said J then is equal to N, Q, V sub D. I kind of want to give you a little bit more of a general description of J because we're going to see it later on in the semester, so I don't want it to surprise you. It also gives you another example of the idea of flux. So that's why I kind of want to show this. So suppose I have some sort of surface. This could be a weird pipe. It could be a wire cut in this manner. And I'm looking at the flow of charge through this side of the system and this side. There's nothing flowing through the lateral surface. So particles of velocity v1 go through this side, and maybe they go through this side here. Okay. I want to know how many particles or how many charges, depending whether I'm talking about water flow or electron flow, how many things flow through this area A1 in some unit time. And I can make this infinitesimal if I want to. Okay. But so how many particles go through that? Right.
Is it the density of particles?
Yes, I need to know the density of the particles and the volume of particles that flow by, right?
Right.
Okay. So I need to know the density of particles and the volume of particles. And then what I could do is make this on an infinitesimal scale. And so let's consider particles that flow through here in a time delta t. Okay. The amount that flow through here through delta t is going to be the velocity of the particles times delta t times A. I'll just write V1 times delta t times A. So this is the volume of particles. This is the number of particles per unit volume. And I forgot my delta t, sorry. Okay. So my V here is just V1 delta t times A1. And if I want to write in general, here, if I want to do it infinitesimally, dV is V1 delta t times dA.
Hey, Professor, one more time. What is N exactly? Is it the number of particles?
The number of particles per unit volume, it's just the density.
Okay, gotcha.
Okay, I lost my, so this is my dV. Well, let me keep it as delta t for now. Okay. And if I want dV dt, and I know I'm not being careful with my deltas and my d's, I just get that. Now on the other side is more complicated because the velocity vector is not perpendicular to the surface. So the only component of V that passes through the surface are those that are perpendicular to the surface. Right? You can always break up a vector into parallel and perpendicular components. Only the component of V parallel to this normal pass through. So V2 has to be written as in terms of a dot product. And this is going to be more general. Okay. This is going to be more general, writing this V2, the V2 on this side. So the number of particles then, there's too many n's. And so really, in general, for me to write the number of, or actually to write the volume, I got to write it like this in general. Okay. Does that make sense? And really, this should be these really should be deltas, and I wasn't careful.
What does n delta big V represent?
Okay, volume times number of particles per unit volume. Just think about it.
Oh, just gives you the number of particles.
That's right. That's right. Okay, so the volume in a time delta t, and I got to write delta v's, and again I'm being sloppy. Really should be written like this, so that it takes into account both surfaces, because what if V is not parallel to n? So you want to write it like this. And then delta V over delta T is n V. I know there's too many n's here. And then if I do this, if I look at this over an infinitesimal area, then everything becomes a D. And so I call this dV dot. The volume per unit time passing through an area is given by this expression.
Isn't it just V dot, or do I not understand the notation correctly?
Yeah, you're right, it is V dot.
Okay.
Okay? So I want to, that's a general way to write the volume of particles passing through. So if I consider the number of particles passing through the right and the number of particles passing, through the left and the number of particles passing through the right, they're going to be the same as long as I don't have anything inside the pipe that takes away or adds to my number of particles. Isn't that true? I mean, let's say I had a battery inside here that produced more electrons. Or if we're talking about water, what if I had a source of water in here? What would happen? Well, more water would come out of here than this side. But let's assume there's no source inside. If there's no source inside, whatever goes in has to be equal to whatever comes out, right?
Yeah.
Okay. So I can then say that this is going to be equal to this. And I can get rid of my delta t's. Okay. If I multiply both sides by q, whatever the charge is on both sides, Then I have the amount of charge per unit time on the left equals the amount of charge per unit time on the right. Correct? The amount of charge per unit time that goes through the left equals the amount of charge per unit time going through the right. Does that make sense?
Yeah, where does the unit of time come from?
Oh, I got rid of the dt, right? Remember that the unit of time comes from the fact that I cancel out the dt. I divide both sides by dt. That's why I have this here.
Right, but I'm just saying, if that expression you have underlined is for something per unit time, shouldn't there be a unit of time like actually in the equation? I guess I'm just confused about that.
Yeah, it's right in the velocity, right? What's velocity?
Oh, right. Okay, cool.
Okay. So the amount of charge per unit time on the left equals what is that called? Amount of charge per unit time. What's that called?
Flow?
Flow. Yeah, it's close. We gave it a name. Coulombs per second. We gave that a name a couple of weeks ago. Current. Charge per unit time is called current. So the current going through the left equals the current through the left or going through the right. Okay. So I can describe the current this way or this way. This is more general because it takes into account the dot product. Now, if I want to look at the amount of current that passes through a dA, if I want to just look at an infinitesimal amount of current that passes through a small area, then I can say, oh, let's look at an area dA. So then di over dA is equal to Q times N times V2 dot N This is the charge per unit area. I want to define a flow. This is really something I would call this as J dot N hat. And I'm going to define J, the vector J, as NQ V2. But let me say, and I forgot to say something about V1 and V2 in this problem. If the density is the same on this end and this end, the velocity has to be the same here and here. If the density of particles is, if the velocity is different here from here, then the density is going to change. And so I want to make V1 to be equal to V2, and so I'm going to call this V. So I'm going to call this thing the current density. Okay, so the current density is actually a vector. Okay, the current density is actually a vector.
The derivative of di over dA, that represents the way that the current changes as you look at different areas, right?
Right.
But if in this problem, wouldn't we expect that to be zero?
It changes. Well, it's not how it changes. It's actually the current per unit area.
Oh, okay.
Okay. And generally, it's constant. The amount of current flowing in any area over any area is constant.
Can you maybe try and briefly explain why current per unit area isn't just I divided by A?
Well, a couple of reasons. One, if the velocity is not perpendicular to the area, let's say you have a material whose properties change so that maybe the electrons have an easy time flowing here, but a harder time flowing out here.
I see. Okay. Thank you. So I over A would work for like something, or does it just never work actually?
It will, well, here's the thing. It will work for almost all the problems we will do in this class.
Gotcha.
Okay. The only reason why I'm bringing this up, because we're not going to do anything with it, is because when we get to chapter 30, we're going to be calculating magnetic fields where we have this thing that varies, and then you might say, well, where does that come from?
Right.
That's all I'm doing here. You're not going to be tested. You're actually not going to be tested on this at all, this stuff. But I want to introduce this to you so that when it comes up in chapter 30, you don't say, where the heck does this come from?
Right.
You see what I mean? Okay. All right, so this is a general description of current density. This was a simple one, but this description that we wrote here is going to work for almost all the problems we do in chapters 20, 27, and 28. Because when we talk about current flowing through a wire, J is constant. Okay? And the current is, the charge is moving perpendicular to any cross-sectional area of the wire. Okay, if you're talking about water flowing through a pipe, then you probably have to use this definition of J. And this V is called the drift velocity of the electron, and that's something I'm going to derive today. Okay. So this discussion, and maybe it took me long to go through it, is just there to get you familiarized with the concept and nothing else. Also to help tie it to the idea of flux. So then the current is just the integral of J dot NdA. And like I said, when we're doing problems with wires, J is going to always be perpendicular to N, and it's going to be constant. So basically end up getting I is J times A. Okay, so I want to develop a simple model of electrons going through a wire. So suppose we have a light bulb connected between the two terminals of the battery. The battery provides energy. It does the electrical work on the electrons. The electrons, kinetic energy, the electrons gain kinetic energy, and as they go through the wire, they collide with the electrons, they collide with the atoms in the wire. So basically, if I were to draw an image, idealized image of a wire, and these are the atoms, okay, in the wire. What's the electron doing? The electron's going through and colliding. I mean, constantly colliding. So what's going to happen to the energy of the electron as it goes through that?
It's going to get lost.
Yeah, it's going to lose its energy. How's that energy going to be dissipated? It's going to produce heat. And if it's going through a filament of a bulb, the bulb will get hot enough that it's going to glow. Because the filament's really narrow, so the energy that's transferred to that little narrow filament is going to cause that filament to get pretty hot, and it'll glow. So the kinetic energy loss of the electrons increases the vibrational energy of the atoms in the metal, and that results in increased temperature. I mean, if you've ever worked with a pretty robust electrical equipment, even a vacuum cleaner, if you run the vacuum cleaner for a while, you can feel that the wire gets warm. Maybe if you work with a drill, for example, a larger drill, you can feel that the wire does get warm. Anything that requires a lot of current, you'll feel that the wire gets warm. That's because the electrons are dumping their energy into the wire. Okay, so I'm going to derive an expression for the drift velocity and do a little bit more with it. This is called a Drude model. It's a very crude model of electrons flowing through a wire. It doesn't have to be electrons flowing through a wire. It can be some charge carrier going through some sort of medium. So suppose we have a wire and we place a potential difference between the ends of the wire. So that potential difference is going to give us an electric field. And of course, that electric field is what's going to cause the acceleration of the electrons, or I can say the charge carriers. So F equals Q times E, which according to Newton's second law gives us ma. We're assuming there's no other forces acting on the charge carriers, which, okay, they're in the wire, they're electrons. I can solve this for A very easily. And A is dV dt. Okay. And then I can solve for V. And of course, the electric field's uniform. This integral is easy. Uniform and constant, I should say. All right, that's what I get when I integrate. Now, what I want to do is calculate the average, because I cannot track, look, I cannot track every single charge carrier that's in a wire, okay? I can't do that. And so what I want to do is, I want to calculate the average value or the average velocity of all the particles that are in the wire. So when I calculate the average velocity, this term is a constant, it's not a big deal. But then the t value I'm going to use to estimate the average value is going to be something called the time between collisions. And if you've had 215, you've done something like this when you talk about kinetic theory. It's the same model. Now this term, what the heck is the average of this number? The average of all the velocity vectors. If you have Avogadro's number of particles in your wire.
Isn't it just basically zero?
Yeah, they're all randomly oriented, so that's zero. This is called a drift velocity. So now we have a model for V that we can put in this equation. So V sub D before I go on, anybody want to guess what that value, this value's approximate value of the drift velocity of the electrons? Anybody want to guess? Basically, the velocity of the electrons as they go through this wire. What do you think that is? Anybody want to guess?
I have no clue.
Okay, I will write it down. It's about, and I'm overestimating it, okay? Does that sound fast or slow?
Slow?
That's about the speed of a bug that's crawling on the ground.
So that means tau has to be like tiny, tiny, tiny. Right? Like the time between collisions is just...
Yeah, it's going to be a small, you're right, it's going to be a small number. But, I mean, does that sound, does it sound intuitive, that number?
No.
I mean, if you think about it, somebody would probably say, wait a minute, so I can probably flip the switch on in my room and then sit in my chair before the light goes on. But that doesn't happen. Why?
Would we have to do this problem relativistically to get a better answer?
Oh, this is a measured number.
Oh.
Right. Granted, this is not accurate because I'm not taking into account quantum mechanics, but this is a measured number. Why is it, I mean, it's really small, so you really don't need relativity. So, I mean, a student will ask me that, you know, I can flip the switch on, sit in the chair and before the light goes on. What's wrong with that?
It's not true.
Yeah, so imagine you have a hose full of water and you turn on the water. Is the water going to come out right away?
No.
It's full of water.
Yeah, if the hose is full, then yeah, it's already primed.
Sorry, I didn't hear you
If
say
it's
this.
full of water, so the wires are full of electrons. And so that's why the light turns on right away. The reason why this number is small, because we're taking this distance divided, I mean, this number is this distance divided by time. And look at the amount of collisions that are undergoing, the electrons undergoing. I mean, obviously in between collisions, that thing is going really fast. You know, we're talking maybe 10 to the 5 meters per second. But because of the number of collisions it undergoes, the time it takes to go from this end to this end is substantially larger. And in fact, and I think on Monday or Tuesday, I'll bring in the demo that illustrates it, a mechanical analog. I'll have a mechanical analog of this so you can see it.
So,
Okay.
Professor, would it be fair to say that the electrons are actually traveling a lot faster than 1 centimeter per second, but because of the collisions along the way, it takes longer to get there? Or is it actually like physically traveling close to 1 centimeter per second?
No, the former is correct. Right?
Okay, because it's an average, right?
Because
It's not
they're
like
going, because they're going about maybe 10 to the 5th meters per second, 10 to the 6th meter per second in between collisions. But because they undergo so many collisions,
Right.
it takes a long time to get from here to here.
I had another question. You said that the reason that it turns on almost immediately is because there's electrons all throughout the wire, you know?
Yes.
What communicates the quote unquote turning on? Is it the electric field? Like it propagates at the speed of light through the wire?
Yes.
Okay.
So that propagates at the speed of light, right? And so that first electron comes, you know, goes through the wire right away, right?
Right, or the
next to
field
the bulb.
causes the electrons at the end of the wire to go immediately.
Yeah, because if you have a wire with no electron, that thing would be highly charged,
Right.
and you would probably get you would feel it if you touched that wire, because it would have a very large electric field. So yeah, it's the same thing as having a hose full of water, and you turn it on, the water comes out pretty much right away. Granted, the information isn't probably propagated as fast in the hose as it is in the wire.
Right.
Yeah. So I'm going to take this equation for the drift velocity. I'm going to put it into that equation. And so I'm going to take the dot product of this with the normal to the surface. So that, or actually, let's not do that yet. Let's just leave it like this. So I want to write J is N times Q times this thing. I'll write it as a vector for now, and later I will not. Let me rearrange this. So it says J is some this whole thing is a constant, times the electric field. Okay? It says that J is some constant times the electric field. Now granted, the value of this constant is probably not accurate because I'm not taking into account quantum mechanics. And even if I did take into account quantum mechanics, I would see that J is proportional to this guy over a limited range. Okay? So this says that the ratio of the magnitude of J over the magnitude of E is this number. This is the more fundamental way to write Ohm's law. Now, if I consider electrons flowing through a wire, J is going to be perpendicular to the normal to any surface. And so I can say I is J times A. And then I can say I is equal to N Q squared tau over M times A times E. And so this is the equation for the current in a wire where I actually put in the expression for V sub D, the drift velocity. And again, this quantity is not very accurate because I used a very crude model. But it does show me, again, the relationship between J and E is proportional. And again, this is the more fundamental way of writing Ohm's law. This quantity I can write in terms of the letter sigma. Oops. Let me put a semicolon there. Let me go on the other board because I'm running out of space. Because otherwise it's going to be hard to understand. I have J is sigma times E. Sigma is equal to N Q squared tau over M. We call sigma the conductivity. Okay. The units are amps per volt meter, also known as a mole per meter. What does mole spell backwards?
Ohm.
Ohm, okay. You'll see why it's called a mole in a minute. It just tells you how well a material will conduct current through a wire. Okay. So this ratio of the magnitude of J over the magnitude of E, saying it's a constant, is Ohm's law. And as long as this ratio is true, independent of E, the material obeys Ohm's law. So this is like Hooke's law or the ideal gas law in physics 215 or chemistry. in that this is only valid for a range of values of E. If you put too big a field on it, then this is not going to work anymore. Well, I should say that this thing will change. Okay? If V is big, this will change. It's not constant anymore. This ratio will still hold, but this is not going to, it's going to have a different value. Okay? Now notice that our sigma looks constant. I mean, this is made of a bunch of constants, but really it isn't because we're not taking into account quantum physics. So let's go back and look at our equation for I, where I took J, dotted it with the normal to the surface, and then multiplied by A. So I can be written as sigma A E. And I'll just keep the other term here. Now look, the electric field is uniform in a wire. And let's see if I can get this to work. E is basically delta V over L. I'm gonna drop the absolute value signs, okay? At least on this term. And so I can write the following. I can write I is equal to sigma A times delta V over L. Or if I solve this for delta V, then I can get delta V hold on a second. Let me just show you a little bit here. Okay, so then if I solve this for delta V, then I'll get L over sigma A times I. And this is called a resistance. So R is defined to be L over sigma A. It's this term that we don't know very well. Okay? This is the property of material, and it's the conductivity. Now we can define something called the resistivity as 1 over sigma. And then we can write that delta V is rho times L over A times I. And resistance then is rho L over A, where rho is the resistivity, which is 1 over this thing, which looks constant, but really isn't. Okay. R is our resistance that we had in Ohm's law. So now we have a theoretical basis to see for R. The only thing is I don't know this really well. I mean, our model shows it's 1 over this thing, but it's not that accurate. Because like I said, I haven't taken into account quantum physics. Okay. So this is where the idea of the resistance comes from. Now think about it. If I have a wire, the longer the wire is, the more collisions electrons go through, then the harder it is for the charge to go through this wire. So a longer wire implies a greater resistance. Now, if I make this thing wider, then the electrons have more paths to go through the wire. So it makes it easy for the electrons to flow if I make the area bigger. And so that makes my resistance smaller. Does that make sense?
Yeah.
And again, the unit per ohm, the unit for resistance is the ohm. The unit for resistivity is an ohm per meter. I'm sorry, not ohm per meter, an ohm meter. Okay, the unit for resistivity is an ohm meter. The unit for conductivity is a mole per meter. That's because they're reciprocal of each other. Somebody decided to change the lettering. Okay. So if you have a conductor, ideally the resistivity for a conductor is 0, but in reality it's not. For a conductor, it's of the order of 10 to the minus 8 ohm meters. For insulators, it's about 10 to the 10th. Okay, ideally be infinite. And so the resistivity then is the ratio of E over J. And over a range of E's, the resistivity is constant. And so those materials obey Ohm's law. Now, rho is not really constant. I mean, rho does vary with temperature. And we can't see that in our equations because we're not taking into account quantum physics. But rho does vary with temperature in a complicated way. Okay. Really what you want to do is, if you want to know what this is, you actually want to do an experiment. Measure this as a function of temperature. The calculation is very difficult. But you can do it and show that using quantum mechanics, you can see the temperature dependence. Okay. But for a limited temperature range, this thing varies linearly. For a limited temperature range, a limited delta T of maybe 100 degrees Celsius for metals, resistivity varies linearly. And we can write the resistivity this way. If you've had 215, you probably see an equation that looks like this. This number is usually about 20 degrees Celsius. And this is the value at 20 degrees Celsius. So this is the value of the resistivity at this temperature. Okay, so you have a linear relationship over limited range of temperature. That range varies depending on the material, but for metals, the range is about 100 degrees Celsius.
Which equation does this model or look similar to from 215?
The change in length as thermal expansion.
Right. Okay. Thank you.
Yeah. So then resistance can be written this way. And I don't know why they don't include the change in length when they write it this way. So my question to you is, would this be of any use? Those of you at 215, would this be of any use if I can get the temperature very linearly? Or if I really could map out the relationship between temperature and resistance?
No.
Well, isn't it true though, that if I mapped out this as a function of temperature, wouldn't I be able to, knowing the resistance, I know the temperature?
Well,
Doesn't this
because
give me a
isn't the
thermometer?
length changing as you change the temperature too?
I'm sorry?
Isn't the length changing as you
Yeah,
change
you're right, and you're right. I mean, again, a more accurate model would take that into account, right?
Oh, well then, yes.
Okay. Yeah, I mean, you can. I mean, there's devices, they're called thermistors. Thermistors are devices that measure temperature based on the change in resistance. So if you look up this term, these measure temperature based on the value of R. So a lot of times what you do is, some materials are very consistent, so you can make a table of R as a function of T. And it's very consistent. Okay? You do the measurement over and over again, and then, you know, for that value of R, you get the same T. And so as long as you know what that table is, then if you know R, you know T. You might not have this relationship, but if you know R, you know T. And as long as that relationship is consistent, then you can use this as a way to measure temperature. Does that make sense? The most accurate thermometer that we have out there right now, I mean, the one that's used practically is one made out of platinum. There is another way to measure temperature accurately, but it's very cumbersome. Okay. But so a lot of people, what they use is platinum. And because the consistency of this the relationship between T and R is quite good.
Does the for higher temperatures, does the quantum mechanical model give you like a more not exact obviously, but a more accurate answer? More precise, I guess.
For higher temperature, I think that's going to depend on the material.
Okay.
And it's going to depend on how complicated. It just depends on what things you can approximate and what things you can't. Okay. Most people just measure these. Most people measure resistivity because it's too hard to calculate, too hard to model. Just like those of you who take 215, the heat capacity or the specific heat, you basically just measure it. You don't really calculate because it's very difficult, although people have modeled it. Now, if we take this and solve for alpha, and this is an average value, if you take this and solve for alpha, alpha is 1 over rho naught times delta rho over delta T. But if you want to know alpha at a specific temperature, then you have to take the limit of this as delta T goes to 0. Typical values for alpha, the coefficient of resistivity is about 10 to minus 3 per Celsius. Okay. Let me check on time. All right. So, Ohm's law, remember, because people forget this, a conducting device obeys Ohm's law, and I'm going to make this window bigger so you can see it clearly. A conducting device obeys Ohm's law when the resistance is independent of the magnitude and the polarity of the applied potential difference or of the applied electric field. So a light bulb does not obey Ohm's law. So next week when I do Ohm's law lab, I'll show you devices called resistors that obey Ohm's law. Okay. So one last topic, batteries convert chemical energy to kinetic energy of the electrons, and as the electrons go through a wire, they collide with the atoms in the wire, and then the wire gets hot, the internal energy increases. And so as the electrons go through the wire, the delta U decreases as Q goes to the resistor because the electrons keep getting slower and slower. So I wanted to find something called the electric power. The electric power is the rate work is done. Well, you learned this in 205. Power is dW dt. Okay. And really the rate of work is done is just current times the potential difference. So electric power P is delta V times I. But because of Ohm's law, I can write this other ways. Because what I can do is eliminate V using Ohm's law, or I can eliminate I using Ohm's law, and I can get the power written in this fashion. Okay, and then the units are joule per second. You folks learned about power in Physics 205. And this is also a watt. So power is defined to be dW over dt. The connection between energy, electrical energy, between electricity and electrical energy and heat really was developed by Joule. Joule actually discovered that. So you will see people who are not in the field of physics or engineering refer to this as this equation in a particular name, which is just just a mnemonic so that students can remember it. Okay. And some people call this Watt's law, which is a mnemonic. Watt died many years before these ideas came around. But for some reason they call it Watt's law. Okay. But don't call it Watt's law, it's not. Okay. Because this is not a law of physics, this comes from a definition. So, let's see how familiar you are with stuff in your house. Which bulb has a greater resistance, a 25 watt bulb or a 100 watt bulb? Anybody want to venture to guess? It's okay to be wrong. Especially on this one.
I'll say 25.
25 watts, okay. Anybody else want to say? Which one has a... that answer is correct, actually. So the question is why? Well, first of all, we need to understand the light bulb in your house. Okay? Because there's a lot of people in my other class didn't know this, but I want to see if you guys know this. The outlet in your house, how many volts is it?
Like 5 or something?
Are you talking about like for the entire house or?
Just the outlet that you would plug in something into it, like your TV or
120, right?
120. So your outlets, most of them are 120. Now granted, this is AC, right? It's not DC. We'll talk about AC later in the semester. So those outlets are 120 volts. That's really, AC varies with time. So this is some sort of average, and I'll talk about what that average is later. It's not really an average. Technically, it's not an average. It's called a root mean square value. But anyway, it's 120 volts. So all light bulbs then that you put in your house, that you screw in a light socket have 120 volts across them. So those ratings are based on the fact that you put 120 volts across the bulb. So I'm going to use this form of the power equation. So now when I look at this, if I want to make the power greater, what must happen to the denominator?
It gets smaller.
It has to get smaller because all the bulbs have 120 volts across them. So the 100 watt bulb has a smaller resistance than the 25 watt bulb, right? The 25 watt bulb has the greatest resistance. Okay? Just from this equation. Of course, you have to know that all the bulbs, all the light bulbs are rated at 120 volts, right? When you look at a bulb, it'll say it's for 120. Okay? So one of the things I want you to be familiar with is stuff in your house this semester. Okay? So your outlets, most of your outlets, the outlets for the, let's see, the air conditioner, the electric oven, your dryer, and if you have an electric charger for your car, they're 240. Okay, because they require a lot more energy. But pretty much all the other outlets are 120. And I might have missed something that's 240. Okay? So every outlet's 120 volts. Okay? And the voltages we're going to be working in the labs are much less than that. We're talking about 1 or 2 volts. So in the module, there's a couple of videos for you to watch. You should watch them so you get more familiarized with voltage and current and things like that, and what's in your house. So I have one on safety, and I'm gonna on Tuesday I'm gonna show you 2 videos that Tyler made. No, one video that Tyler made. I'm gonna do in a demo on electrical safety. We're gonna run the current through a hot dog and see what happens to the hot dog. Okay. All right. I want to do one more example, and then I'll answer questions from you. So most of the stuff in the assignment is pretty straightforward. Some conceptual questions, just to get you familiarized with Ohm's law. And look, some of the details that I went through, good to know conceptually, but to know the theory behind them is kind of a challenge because you need to know some quantum physics. So let's say I have a circuit with a resistor, a meter that is hooked up in series. This resistor is 45 ohms. This is 9 volts. And this is measuring current. So I want to know how much current is going through my circuit. I want to know how much power is being dissipated, how much energy I've used up in 15 minutes, how much charge was delivered by the battery in 15 minutes. So I'm going to use Ohm's law to solve for I. That's easy, delta V over R. So this is going to give me 9 volts. Or 45 ohms. And so 9 over 45 is 0.2 amps. I'm not being very good with sig figs here, but okay. The electric power, I have 3 ways to calculate electric power. 1, 2, 3. This is the amount of energy per unit time that is used up by the resistor. What that means is if I take out the power supply, there's no current, because this uses it all up. Okay, and again, I'm ignoring the fact that the wires have any resistance. I should say that the resistance of the wires is much lower than the resistance of the resistor. This could be a bulb or whatever. Okay, If it is a bulb, then I'm saying that the resistance at 9 volts is 45 ohms. Okay, let's calculate the power. The power is delta V times I, and delta V is 9 volts times 0.2 amps. 9 times 2 is 18, 1.8 watts. Next question is, what is the power, what is delta Q? Well, I is dq over dt, but I is constant, so I can also say I can approximate it as delta Q over delta T. Actually, it is the same thing because it's constant. So then delta Q is I delta T. If it wasn't constant, then this would be an integral. So I is 0.2 amps. And delta T is 15 minutes. How many seconds in 15 minutes? Because this is a coulomb per second, right? How many seconds in 15 minutes? 60 times 15 is 900 seconds. So this comes out to what? 180 coulombs. How much energy is delivered by the battery in 15 minutes? So if power is dW dt and power is constant, then the energy is power times delta T. So it's going to be the power of 1.8 watts times 900 seconds, 1620 joules. There's actually another way to get this, because this delivers 9 joules per coulomb, and I've delivered 180 coulombs. So 180 times 9 is 180 times 9 is 1620 joules. Oh, and then one thing I forgot there is, I want it in kilowatt hour. What's a kilowatt hour? Do you folks look at your electric bill? No? A kilowatt hour is energy. It's 1,000 watts times 1 hour, which is 3,600 seconds. So 1 kilowatt hour is 1,000 watts, which is 1,000 joules per second, times the number of seconds in an hour. And that gives you 3.6 times 10 to the 6 joules. So how many kilowatt hours is this? Well, I got to take, so the number of kilowatt hours for a light bulb is going to be 1620 joules over 3.6 times 10 to the 6 joules per kilowatt hour. And you can see it's a fairly small number. I don't have the value with me here. Let me calculate it. Not going to cost you a lot, right? Because you folks are charged by kilowatt hour, right? From PG&E. That's unless you have solar power. Okay, so that's how much it would cost. That's how many kilowatt hours. You multiply that by the cost per kilowatt hour, and it will tell you how much you would have to pay for that. Questions on this? Okay. Do you have questions on the multimeter quiz? Do you have questions before the exam?
Oh yeah.
Okay, go ahead. We got a few minutes.
So the first one is the number 5 on the multiple choice for the practice exam. It's the if you do positive work to move a charge in an electric field, its potential energy increases.
Oh, did I type the wrong answer? Let me look for the key. Did I type that wrong? Hold on a second. Somebody asked me about that. I think I typed the wrong answer.
I think it was the conceptual question that was wrong. I don't know if the exam was actually incorrect.
Just give me a minute. I gotta find the file.
Yeah, take your time.
If you do positive work to move a charge from A to B, if you do positive work, the potential energy increases.
Oh, okay. Yeah, I didn't comprehend the if you do positive work part.
Yeah.
It's like lifting a pen up increases the potential energy from the gravitational field, right?
Yeah.
Yeah, okay. That makes sense then.
Okay. The work done by the field would be negative, right?
Right.
Okay.
Oh, another question I had if no one else has one is number 1. If you bring a charged rod near an uncharged sphere, it's the answer is it'll be attracted only if the rod's a conductor.
Should be C.
Yeah, that's what I thought, but then I think the answer on the key is A.
Okay, it should be C. Sorry
Okay.
about that.
No, it's okay. That's why I'm asking. It's not a big deal.
I gotta change it though.
Right.
If I don't change it now, I'll forget. Okay. All right, thank you. Any other ones? Yeah, and I was trying to hurry giving you guys this. That's why I just give you that video link.
You went through the videos. The video has all of the short response questions, right?
The video has part 2 if I remember correctly.
Then yeah, I have all my questions answered.
Okay. Any other question?
What's going to be on the exam?
Everything. The material from chapters 23 through 25, I guess. I don't tell people usually when I have a problem like this on the exam, specifically because then students will only study for various problems. And really the goal here is to really understand the concepts well. Because if you're trying to just memorize certain problems, that's not going to help you understand the topics, especially when you take a higher level course, whether it's in physics or engineering, because a lot of times it's a quantum leap, and if you don't learn the fundamentals, it's really hard at the junior or senior level. Because I remember going from freshman level physics or these intro courses to the junior senior level ones. It's a quantum leap if you don't have your fundamentals down. Yeah,
I'm just struggling.
Yeah, it's not an easy unit. I mean, I remember taking a course like this. The exam averages were low, but we all got through the course. He covered everything anyway. The professor I had, he would give us, his quizzes were like 3 hours. He would tell us to bring our lunch. He would call them quizzes, but they really weren't quizzes. There would be 3 problems, and each one had like parts A through F.
If we have a question between now and the exam, are you going to be able to answer them?
I'll try. Okay, I'll be around. I might have to step out for a little errand, but then I'll be around. Okay.
All right. Thank you.
I'll try the best I can to answer questions. All right. Anything else? I think I'm going to send you the modified, the changes to the key to the practice test, at least the conceptual questions, because I screwed that one. I typed the wrong answer in. All right, so if you don't have any more questions, we'll see you at 2.
All right. Thank you.
All right, you're welcome.